Hi, Matrix. How you guys doing? I hope everybody is doing well and that we're keeping warm. It seems as though we have a bit of a cold front. It's been raining a lot where I'm at, and I just hope that we are ready and equipped to jump straight into the session. My name is Muranga, and I'm pleased to be continuing on with the prelim prep that we started with last time. Hopefully, you guys are finding all these prelim preparation live lessons very helpful and that you are actually enjoying them and taking away some useful information that will help you guys in the upcoming prelim sessions. Welcome, guys. Welcome, welcome. From the last time we had started, we had gone through the first half of the paper, of the prelim paper. We did the multiple choice. We went on to do organic chemistry, a lot of that. If you guys did miss out on this, please do check out our YouTube channel. That's where we do post the recordings of these sessions. Today, we are going to jump straight into question 5. We continue on from last time. We did start out a bit with this question, but we didn't get enough time to finish it. And I do find it very beneficial, or I do think that a lot of us will stand to benefit if we go through this question once again. So we have question 5 here. You guys can see the words on screen, right? But I'll just zoom in just to read the whole scenario. And yeah. So question 5 reads as follows. The reaction between sodium thiosulfate and excess hydrochloric acid is used to investigate the effect of concentration and temperature on the rate of reaction. So right now, I'm quickly going to highlight excess hydrochloric acid. That's very important. We cannot forget that. Excess hydrochloric acid. And now we have the reaction given over there. And they go on to tell us an Erlenmeyer flask is placed on a white paper marked with a light cross on it. The time taken for the visibility of the cross to disappear is measured. See the diagram below. The diagram just kind of indicates what's happening. Let me scroll to that right now. Sorry, it's just, I think my screen's a bit frozen. I apologize for that. Just give me a second. Okay, my screen. Oh, yeah, sorry. I'm not sure why exactly, but my screen is frozen. Might have to just exit and reopen. Sorry for the inconvenience, guys. Oh, sorry. Yeah, there we go. Cool. So let me just reread it. Sorry for the inconvenience. The reaction between sodium thiosulfate and excess hydrochloric acid is used to investigate the effect of concentration and temperature on the rate of reaction. The balance equation for this reaction is given, and they tell us that an Erlenmeyer flask is placed on a white paper marked with a light cross on it. The time taken for the visibility of the cross X to disappear is measured. See the diagram below. You are given the diagram. 5.4, well, before we get there, we're told here that the same volume of sodium thiosulfate was used for all 3 reactions, and then they give us the table showing the reaction conditions. I can see that there's a difference in concentration between 1 and 2, and 2 and 3. There's also a change in temperature that happens solely for reaction 3. So we have to keep all of this in mind when answering the follow-up questions. Now, they tell us here that experiments 1 and 3 are now compared. They go on to tell us that the Maxwell-Boltzmann curves for the distributions are shown below. And now 5.4.1 is asking, which reaction, which experiment 1 or 3 is represented by curve T2? Which one do you guys think is T2? Do you guys think it's experiment 1 or 3? In this case, let me highlight the stuff just to show you guys exactly what changes or differences we're looking for. So the difference I can see between experiment 1 and 3 is that there's a change in temperature. Experiment 3 has a higher temperature, and now we have to now relate that higher temperature to one of the curves on the Maxwell-Boltzmann energy distributions. Do you guys think experiment 1 or experiment 3 represents curve T2? Please drop your answers in chat. What do you guys think? Experiment 1 or 3, does that represent curve T2? Okay, the answers are rolling in. Yes, it is indeed experiment 3. That is correct. Well done to everybody that tried. To those that didn't get it correct, let's now go through the reasoning. So what we should note is that, oh, well, 5.4.2 kind of asks us for the follow-up. So for curve T2, what we need to see is that, I'm just going to draw this EA. That EA just means activation energy. And I just want to zoom in and show you guys what exactly I use to determine that this is indeed experiment, or T2 is indeed experiment 3. So what we should remember is that whenever we have a higher temperature, we know that the kinetic energy of all particles has increased. If you have a higher kinetic energy of all particles, we know that we have more particles with sufficient energy. If they have sufficient energy, they have more than the activation energy, and therefore we have more effective collisions per unit time, or in other words, we have more successful reactions. I'm going to highlight or kind of shade in the areas under the graphs. So I have firstly the area under curve T2 being red, and then I want to shade in the area under T1 in green. The area under T1 in green is over there. And what we see is that T2 has a higher area under the graph. So we can relate that to more successful collisions because you have more particles having sufficient energy, being more than the activation energy. And that's how I would kind of deliberate or choose and answer this question. So let's write down the bullet points over here as to how we would actually answer this in such a manner that we get the marks. So for this question, we'll say that for temperature 2, or not, for curve T2, sorry, it has a higher temperature. Or we should know that a higher temperature equals more kinetic energy for the particles. So that'd be our first mark. Our second mark would come from saying that if we'll have a greater number of particles with sufficient energy because we just have more kinetic energy of the particles. Hopefully that makes sense. So I'll say here that you'll have an increase in the number of particles with sufficient energy, or with energy higher than the activation energy. And then our last mark would come from saying we therefore have more effective collisions per unit time. Cool. So I think this one was quite straightforward. Let's move into question 5.4.3. They ask us to sketch the curve of T2 only in the answer book and indicate the effect that a catalyst would have on the EA or activation energy. I want to pose this question to you guys in the chat. What exactly does a catalyst do to the activation energy? Drop your answers in chat. What does a catalyst do to the activation energy? Yeah, so the first answer that I see is correct. Well done. It lowers the activation energy, guys. So what that would look like is the following, if I had to sketch that. So I'm just going to try my best to mirror the curve T2. And now our activation energy would be lowered. So instead of it being where the red point is, so instead of it being like here where it's red, our new activation energy would instead be over here. So this would be our old activation energy. And this would be our new one over here. So I'm just kind of showing you guys what's going to happen. So in order for us to get our marks, we would actually have to sketch in our old and our new activation energy. I also have another answer in chat. It provides an alternative pathway. I think, yes, that can be taken as an answer. But the main thing is, yes, it lowers the activation energy. This is what we'd see on the curve. So for our 2 marks, we'd have to draw in our 2 activation energies. We show the old one and we show the new one. You have to make sure that the new one is lower or before the old one. Are we all good on that? Can I get a thumbs up? Can we carry onwards? Okay, I'm seeing thumbs up. I'm going to move onwards then. Now let's get into 5.5. We are told that 0.7118 grams of sodium thiosulfate reacted completely with hydrochloric acid in experiment 1 in 34 seconds. Calculate the rate at which hydrochloric acid reacted in experiment 1 in moles per second. The volume of hydrochloric acid used in experiment 1 is now doubled. All other reaction conditions remain the same. So for a question like this, let's jump straight into it. So the first thing that we're going to want to do is we're just going to take the information given to us, and I'm going to convert that into moles now. Okay? I want to take what has been given, convert it into moles. So right now, I'm then going to have N is equals to mass over molar mass. Remember, guys, you get a mark for the correct formula. In the next case, my mass is going to be the given 0.7118 grams. And my molar mass, I have to calculate that. I have to find that. In the chat, guys, I want to ask you, what is the molar mass of sodium thiosulfate? Let's try get that. Because we want to end up finding the moles of sodium thiosulfate, Na2S2O3. Yes, we have an answer. It is 158 grams per mole. So I substitute that in, and now to get the moles of sodium thiosulfate, I will have 4, 505 times 10 to the power of -3 moles. Great. From here, I want to now get the moles of hydrochloric acid. How do you guys think I might get that? Let's go back to my reaction and let me find my ratio. In this case, I see that I have 1 sodium thiosulfate for every 2 hydrochloric acids. So I have a ratio of 1 to 2. So let me write that down. This gives us 1 is to 2. And now to get the moles of hydrochloric acid, it's simply going to be 2 times the moles of sodium thiosulfate. And that then gives me 9,01 times 10 to the power of -3 moles. Cool. As it is, we are not done. We've only done 3 marks worth of work. We still need to find the other 2 marks. We haven't found the rate at which all this reacts. Let's get the rate. So the rate over here, they ask us for the rate in moles per second. So in our case, I'm just gonna have it as the change in mole over the change in time. Okay? I'll then have, let me do rather negative change in mole so that I get a positive rate. My initial mole of, in my case, hydrochloric acid, or my final mole of hydrochloric acid would be 0. My initial would be 9,01 times 10 to the power of -3. And then the change in time, in this case, is just going to be 34 seconds. That's given to us. My negative is outside just to make sure that I end up with a positive answer. And I then end up getting my rate to be 2,65 times 10 to the power of -4 moles per second. Remember, rate is just delta whatever over delta the next thing. You can think of it as kind of like your gradient. Your gradient, you know, it's the change in y over change in x. So in this case, you're gonna have to take the change in moles over the change in time. Okay? Right. So that's what we have for this question. Our last 2 marks will come from calculating the actual rate. This is the answer. Let's carry onwards to the next one. 5.6 asks us, how would the reaction rate be affected by the change in volume? Would it decrease, increase, or remain the same? What do you guys think? How does changing the volume affect the reaction rate? Is there a change? If so, would it increase or decrease? So firstly, in the chat, do you guys think it'll increase, decrease, or remain the same? Okay, I'm seeing 2 answers already. The first answer says remain the same. The second answer says increase. Let me just wait and see if we have more answers rolling in and see where everybody's heads are at. So the majority of the answers that are coming in are remain the same. That is correct. It would remain the same. Right. And the reason is changing the volume doesn't necessarily do anything to shift what's going on. If you want to maybe, it doesn't necessarily have an effect on this. We still have the same amount of limiting reagent going on. or present. We still have the same temperature. We still have the same number of particles as a whole. What you're doing by changing the volume is perhaps changing the concentration, but you still have the same number of particles present. Changing the volume doesn't have an effect on the reaction rate. That's what we just need to recall and remember moving forward. So that's that for question 5 or the remainder of question 5. If you have any questions, please do pop them in the Q&A section. I'll make every effort to answer them. Otherwise, if I can't answer, hopefully pop them in chat and your fellow attendees can answer you with that. But let's move onwards though. Let's look at 6.1. We are told that we're given a reversible reaction and it can be used to demonstrate how certain factors influence chemical equilibrium. We're given the reaction over there, and 6.1.1 asks us to define the term reversible reaction. A reversible reaction is a reaction in which products can be converted back into reactants and vice versa. That's just a definition. All right, let's move onwards. Let's go to the next question. We are told that the solution is initially blue. We have to write down either turns more blue or turns more pink to describe what happens to the reaction mixture if some cobalt chloride is added, COCl4. Do you guys think it'll turn the solution more blue or more pink if we add whatever they've given us? The answers are rolling in. It does indeed turn the solution more pink. And let's go through why exactly that is. So with this one, it turns it more pink because if we add that COCl4, we're favoring the forward. We're favoring the reaction that pushes it towards the pink side. If you add the COCl4, the reaction wants to use it all up, and therefore it's gonna push and make it more pink by going more towards the right side. We are favoring the forward. Well done to everybody that got that correct. And now the next question asks us, what happens if we add concentrated HCl, hydrochloric acid? Does it turn our solution more blue or does it turn our solution more pink? So the next question, if we add concentrated HCl, does it turn it more blue or more pink? The answers are rolling in. Yes, it turns it more blue. The reason is if you add HCl, we know it breaks apart into the H plus and the Cl minus. That Cl minus is on this side, and if we add more of this here, the reaction wants to use it up, and the only way to use it up is if it goes and shifted more towards the left side of the reaction, we shift more towards blue. Our reverse is being favored. Is that clear? Are we clear on that? Okay, getting thumbs up. That's very encouraging. Let's move on with them. Now, we are told that the test tube containing the reaction mixture is placed in a hot water bath. It is observed that the solution becomes more blue. Is the forward reaction exothermic or endothermic? If we place the test tube containing the reaction mixture in a hot water bath and we observe that it turns more blue, does it mean that the forward reaction is exothermic or endothermic? What do you guys think? Okay, the answers are rolling in, and they are all correct. It is indeed exothermic. And now let's see why exactly that is. So, if we observe that the mixture becomes more blue if we place it in a hot water bath, what in actual fact is happening is that the endothermic is favored. Whenever we increase the temperature, the endothermic reaction is favored. In this case, we see that there's more blue happening, so we'll therefore be able to state that the reverse is endothermic. And if you know that the reverse is endothermic, the forward has to be the opposite, which is exothermic. So let me write that down so we can actually see what's happening. So I'm going to write as my first bullet point, more heat equals the endothermic reaction being favored. Cool. In this case, we have more blue. So if you see that the mixture becomes more blue, it just indicates to us that the reverse reaction is endothermic. And then therefore, the forward is exothermic. Cool. So that's what we have for that. Um, how are we so far? Are we following along? Are we good? Can I get a thumbs up reaction? Cool. So I'm going to move onwards then. For the next question, this is an 8-mark question, by the way. We are told that 3,01 times 10 to the power of 23 molecules, remember, of N2O4 are sealed into a 4 decimeter cubed container and then heated to 400 Kelvin. The following balanced reaction represents the reaction that reaches equilibrium in the container at 400 Kelvin. At equilibrium, it is found that 0.4 moles of N2O4 have decomposed into NO2. Calculate the equilibrium constant, Kc, at 400 Kelvin. So the first thing we have to do for this question is let's actually get the moles present. What they might kind of trick you guys into thinking is that that number given represents moles, but in actual fact, it's the number of molecules. Okay? And now, in order to do that, we're going to use the following formula. We're going to have N is equals to N, number of molecules or particles, over Na being our constant. Na is our constant. If I substitute in the appropriate values, I will then have 3,01 times 10 to the power of 23 all over 6,02 times 10 to the power of 23. Cool. If I simplify this, I then end up with 0.5 moles of N2O4. This is what we actually have. Okay? And now what you guys should be thinking or recalling or jumping to doing in a scenario like this is our rice table. So let's set that up then. All right. So I'm going to do my rice table in terms of moles. I'm going to have now N2O4 over there. On the other side, I have NO2, and I'm going to write in R for the ratio, I for initial, C for the change, and then E for what we have at equilibrium. So what we have here is that number given is the initial number of molecules that we then convert into the initial number of moles. So initially, we know that we have 0.5 moles of N2O4. Let's write down the ratio, though. The ratio is 1 is to 2. This is very important. Now, I want to write in my initial. I know initially I have 0.5 moles of N2O4, but I have 0 moles of NO2 initially. Because what's happening is that we're just sealing all of this. We're sealing this right here into a container only, and then that then reacts to produce that over there. So I know initially I have 0 moles of NO2. Cool. Now let's look at what else is there. We're told that at equilibrium, 0.4 moles of N2O4 has decomposed to NO2. That's very important. If this is the amount that has decomposed, they're telling us that's the change. So the change in this case would be minus 0.4. Then if we now go to the change of NO2, that has to happen according to the ratio now. If 0.4 moles of N2O4 decomposed, that means we need 0.8 of NO2 that has now formed, or the change, the increase in that. Okay? Now let's actually get the moles at equilibrium. For N2O4, it's going to be 0.5 minus 0.4, which is 0.1. Then for the NO2, it's going to be 0 plus 2 times 0.4 is 0.8, which is just 0.8 right there. We have a question. Why is 0.4 negative? It's negative because of the statement right here. At equilibrium, it is found that 0.4 moles of N2O4 have decomposed. So 0.4 moles of N2O4 have decomposed. That they're telling us that's how much of it decomposed. And if they say it decomposed, it kind of reacted to become this over there. Are you good on that? Can I see a thumbs up? 0.4 is not for equilibrium, like I just explained. We are told that at equilibrium, 0.4 have decomposed to that. They didn't say that it decomposed and we are left with 0.4. It says that 0.4 of it decomposed. All right? Is that good? Yeah, if it says that it decomposed and you're left with 0.4, then you know at equilibrium you have 0.4. But in this case, they told us that 0.4 of it decomposed. Then you know that 0.4 of it reacted to form NO2. Okay. Right. So I just need you to note that the values in the table are in moles. So I'm just gonna put a star over here and do it in moles. You could have also chosen to work out the rice table in terms of concentration. You'll just see how that works. But moles just be easier. So this is what we have at equilibrium. 0.1 moles of N2O4 and then 0.8 moles of NO2. Let's get our concentrations at equilibrium now. So I'm gonna just draw a line there, and I'm putting these square brackets just to indicate concentration. And now for the concentration at equilibrium, we are gonna have 0.1 over the volume. The volume in this case is 4 decimeters. So I know my concentration at equilibrium is gonna be 0.025 for N2O4. If I move on to NO2, it's going to be 0.8 over 4. And know that the concentration at equilibrium of NO2 is going to be 0.2 moles per decimeter. So maybe let me write mole over here and mole there. Just want to draw a line separating this. And then this is moles per decimeter cubed. And then this over here is moles per decimeter cubed as well. Right. So now we have our concentrations at equilibrium. Let's now go on to find our equilibrium constants, or constant in this case. Kc, we know, is the concentration of our products over the concentration of our reactants. So our products in this case is NO2. I have to raise that to the power of 2. That power of 2 comes from this over there. Right. And then now for the N2O4, I just fill that in accordingly. And I just want to pose this to you guys. Calculate the equilibrium constant value for me. And let's see if we're still all on the right track. So if you are calculating that, you'll see that the equilibrium constant value would be the following. And we end up with a value of 1,6. No units, by the way. Okay, now I do see a couple of questions. Let me try see if I can answer them. Why are we converting the number of moles? Okay, so I'm not too sure what you mean by number of moles. We're converting the number of molecules. Remember, molecules does not equal moles. Molecules is just the total number of molecules or particles present. We have to convert that into moles by using Avogadro's constant. That's how we have N is equals to N over NA. We can't work with this number because this is not moles. This is just molecules. That's why we convert. Let's see. You don't understand where the 0 comes from? Initially, you have 0 products. All we have is just this. And you seal that into a container and let it to react to form the products. Initially, you have 0 products. Hopefully that answers your question. Let's see. Remember for us to We do use the concentrations for the Kc values, yes, correct. And yeah, to those who are asking questions, are your questions now resolved before we move onwards? Can I get a thumbs up? Okay, great. So that's how we would do a question like this for 8 marks. I guarantee you guys it's not that difficult. We just have to remember key things. If it's a scenario like this, you have initially zero product. If all you have is just the reactants and you're sealing that into a container. We also have to recall that the change that happens in terms of the amount is in proportion to the ratios. We have negative change for N2O4 because N2O4 is decomposing to form our product of NO2. That's why it's negative 0.4. Whereas on the other side, it's positive 2 times that because it happens according to the ratio. And yeah, we just calculate everything else accordingly. I see there's a thumbs down. Could you ask specifically what your question is before I move onwards? How do I get 0.5? I converted the number of molecules into moles. Molecules does not equals moles. Okay? You can think of moles as like a set of something. The same way you can have 1 dozen eggs, a dozen being 12. So if you have a dozen eggs, you have 12 eggs in total, but that's a single dozen. Are you with me? Moles kind of works like that. In 1 mole, you have 6,02 times 10 to the power of 23 molecules or particles in that. Hopefully that makes sense. Again, we're not converting the number of moles. We're converting the number of molecules. I've written it over here. The number of molecules is not your number of moles. And try to think of it in the case of dozen. You can have a dozen eggs. You can have 1 dozen eggs, but in actuality, you have 12 eggs. But when it comes to chemistry, we work with the set, or we work with that. Um, can I call it set of moles? That's not the same as molecules. Are you with me? Can we move onwards now? Okay, I'm seeing thumbs up. I'm going to carry onwards. Okay, the question is, why am I converting number of moles to concentration? You need equilibrium constant is calculated in terms of concentration. So you work in terms of the concentrations at equilibrium to get the equilibrium constant. That's why we convert the moles of whatever we have at equilibrium to concentrations. We can plug that into our Kc formula. Hopefully that makes sense. Now I need to carry onwards. 7.1 tells us that the equations below show the reactions occurring in hydrochloric acid and ethanoic acid solutions. Both acids have a concentration of 1 mole per decimeter cubed and are kept at a temperature of 25 degrees Celsius. We have reaction 1 given there. We have reaction 2 given as well. And we also given the Ka values for each of the reactions respectively. 7.1.1 asks us to define an acid according to the Lowry-Brownsted theory. So an acid according to the Lowry-Brownsted theory, thank you to the person who answered in chat, an acid is a proton donor. Okay? So that's that. By remembering the definitions, you guarantee your guys marks. You guarantee yourself marks. So yes, an acid is a proton donor. Let's carry onwards. We have 7.1.2. Write down one conjugate pair, acid base pair, or acid pair base pair in reaction one. So for 7.1.2, we have two options. I'm gonna now show you the first option. I can have hydrochloric acid and the chlorine ion, or I can have water and this H3O plus. So we have two options for this. And both options would still grant you the marks. Quickly in chat, just a bit of trivia of what we have listed in reactions 1 and 2. Which can I say substance is the ampholyte? Do you guys recall what an ampholyte is? Sometimes they can ask you questions like this, asking you what the ampholyte is. Do we know what that is? So yeah, an ampholyte is a molecule that can act as either an acid or a base by either donating or accepting a proton. That is correct. Thank you to everybody who answered in chat. And it is water. Water can act as an acid or a base, depending on the reaction. Okay. I see a question. I will circle back at the end. I do want to make sure I can get through the paper without rushing towards the end. So yeah, we have our acid pair and base pairs in reaction one over there. What we can see is that our acid, hydrochloric acid, once that donates the proton, what's left of it is the conjugate base. With our water, once it accepts the proton, what it becomes is the conjugate acid. Cool. Now let's move on to the following question. Which solution, 1 or 2, will have the lower pH value? Is it solution 1 or is it solution 2? Which one do you guys think will have the lower pH value? The answers are rolling in. It seems as though everybody's on the same page. It is solution 1. And let's go through the reasons why. So what we will see is that hydrochloric acid is a stronger acid than ethanoic acid because hydrochloric acid has the higher Ka value. If you look at the 10 or times 10 over there, you'll see that Ka for hydrochloric acid is to the power of 6, whereas for ethanoic acid, it is to the power of -5. So we see that solution 1 has the higher Ka value. So let's go through the reasoning here. So you get 1 mark for the correct answer. Our other marks will come from stating that HCl is a stronger acid. So with this, how do you know that? You can say that HCl has a higher Ka value. And then our second mark would come from stating that HCl will produce a higher concentration of H3O plus. Yeah, and that's what we have. So we also what we should, or hopefully, you guys have guys have been accustomed with the list of strong and weak acids and bases, and so that would prove useful in a question like this. But they've also given us the Ka values over here, the ionization constant values, to use to substantiate our answers as well. All right, now let's move on to 7.2. We are told that 10 cubic centimeters of 1 mole per decimeter cubed sodium hydroxide solution is diluted with water until its pH is 13. Calculate the number of moles of sodium hydroxide in the 10 cubic centimeters um, of the initial solution. For 3 marks, whenever you see a 3-mark question, it is a simple formula substitution and answer type of question. So for this one, I do trust you guys will be able to do that. And I want to give that to you guys as a challenge. What is the number of moles of the sodium hydroxide solution in 10 cubic centimeters? Yeah, the answers are rolling in. It is indeed 0.01 moles. So I'll have over here N is equals to C times V. And now our concentration has been given as 1 mole per decimeter. Our volume hasn't been given in standard units. I have to convert that. So that'll be 10 times 10 to the power of negative 3. And that'll then give me 0.01 moles. Cool. Let's move on to 7.2.2. Let's calculate the volume of the diluted solution in cubic decimeters, whereby all of the diluted sodium hydroxide is poured into a burette during a titration. 15 cubic centimeters of oxalic acid of concentration 0.09 moles per decimeter cube is exactly neutralized by a certain volume of the diluted sodium hydroxide solution. The balanced equation for the reaction is given over there. And yeah, we have to now calculate this. So when given a question like this, I kind of think of it as like a 4-step question or 4-part question. So number 1, I need to remember that my pH is equals to negative log of my concentration of H3O plus. Cool. Number 2 is I now look at Kw, and I know that Kw is equals to my concentration of hydroxide ion multiplied by my concentration of hydronium ion. Number 3, I have to now relate the concentration of hydroxide to the concentration of sodium hydroxide, which in our case, we should note it as 1:1. How do I know that? I know that I have one hydroxide ion for every sodium hydroxide. You can see it over here. Um, and then lastly, I have to use the concentration of the sodium hydroxide I get to get the actual volume. So let's go through it then. Let's actually calculate what we need over here. So we would have gotten 1 mark for writing this down. Our next mark is by actually doing the calculation. So from here, we are given the pH of 13 right there. So maybe let me zoom out a bit so everything can be in view. And now from there, I know that 13 is equals to minus log my concentration of H2O plus. If I simplify this, I end up getting my concentration of H3O plus being equals to 1 times 10 to the power of negative 13 moles per decimeter cubed. I'm running out of space a bit. My apologies for that, but let's carry on it. So what's next is I need to now get or now do the KW formula. So from here, I know that 1 times 10 to the power 14 is equals to my concentration of hydroxide ions multiplied by my concentration of my H3O plus. I found my concentration of H3O plus. Maybe let me highlight that. This value over here goes into there. And now from here, I know that therefore my concentration of hydroxide ion will be equals to 0.1 mole per decimeter cubed. I just get the 0.1 by just doing simple algebra. Are we all clear on that? Are we good so far? Can I get a thumbs up? Cool. Now let's move on to our third step. I know that my concentration of hydroxide is going to be the same as sodium hydroxide. They have a ratio of essentially 1:1 in this case. So with that in mind, I know that the concentration of OH minus is equal to the concentration of NaOH, which is equals to 0.1 moles per decimeter cubed. Right. And now from there, now that I have this value, I can equate it and put that into this formula over here, whereby I have 0.1 is equals to my moles of sodium hydroxide, which I did find earlier. It's this over there. I'm going to substitute that in. And then that's then divided by V for the volume. But we don't know the volume as of yet. And now with the volume being the unknown variable, I just do some simple algebra. And I then end up with V being equals to 0.1 cubic decimeters. Cool. So that's how we would do a question like this for 5 marks. I do it's a 4-step question, essentially. Number 1 is recall your formula. pH is equals to minus log concentration of H3O plus. From then we look at Kw. Kw is not called the ionization constant of water, if I remember correctly. And that's just going to be 1 times 10 to the power 14 is equals to your concentration of your OH minus multiplied by your concentration of H2O plus. That is the second step. Our third step is we look at the ratio of OH to NaOH. We know that within 1 mole of NaOH, I have a single OH present. So it's 1-to-1 essentially, and I can therefore conclude that my concentration of sodium hydroxide, NaOH, is also going to be 0.1 moles per decimeter cubed. I can then use that value in my C is equals to N over V formula, and I end up getting my V, which is my volume, to be 0.1 cubic decimeters. How are we so far? Are we following along? The 13 is the pH. Remember, they told us that the pH is 13. I'm just answering one of the questions popped into chat. This 13 given here as the pH is what we use over there. All right. And then in the Q&A, I just have question marks. Please be specific. I can't even help you if you send just only question marks. I wish I could understand what you want me to say. So yeah, cool. Now that you get that, to the person who asked about the pH or where the 13 comes from, I'm glad that everything's cleared up. Before we move onwards, because I do understand that this looks a bit complicated or a bit much. How are we? Do we have any questions? To the person asking, we use that more. I'm not too sure what you mean. Could you please be more specific? If we don't have any questions, can I move onwards? Can I see a thumbs up? How did we, okay, the question, somebody's asking, how did we get the concentration of OH minus to be 0.1? Step 2. Step 2 is how we got that. Step 2 has Kw is equals to the concentration of OH minus multiplied by the concentration of H3O plus. I found my concentration of H3O plus from the previous step, step 1. I use that in step 2. And that's how I get the concentration of OH minus to be equals to 0.1. Hopefully that tracks. We use the moles calculated in 7.2.1. Yes, we do use that for step 4. It's very rare that they ask us to calculate something and there's no chance of it being somewhat used in a follow-up question or to at least explain or something like that. To those who are asking questions, are we good now? Can I move onwards? Okay, great. Now let's move on to the next question. Right there, we are going straight into electrochemistry now. A lot of you guys think of electrochem as this intensely difficult topic, of which it really is not. hopefully by the end of the session, we will be a bit clearer on that. So we are told that a galvanic cell is set up under standard conditions using Haas cells A and B shown below. 8.1 asks us to define oxidation in terms of electron transfer. And in the chat, guys, what is oxidation in terms of electron transfer? Yeah, it is the loss of electrons. Well done. It is indeed the loss of electrons. So let's carry onwards then. Um, what are the standard conditions? Let me ask that first. What are the standard conditions of a galvanic cell? Yes, the answers are coming in. It is 25 degrees Celsius as the temperature, correct? Pressure of 1 kilopascal and a concentration of 1 mole per decimeter cubed of the electrolytes. Yes, that is indeed correct. It's not 1 atmosphere, actually, a pressure of 1 atmosphere, not 1 kilopascal, sorry. So let's now move onwards. 8.2 asks us to write down the initial concentration of the H plus in the aqueous solution in half cell B. This is why I asked us the standard conditions. The answer to this one is simply going to be 1 mole per decimeter cube. Cool. 8.2 asks us to name the metal used as the electrode in half cell B. What is that metal going to be? The answers that I am seeing are correct. It is platinum. Great. And now let's look at 8.2.3. What is the formula of the reducing agent? Or in other words, what is the formula of the thing undergoing oxidation? The answers are rolling in. It seems as though everybody is on the same page. It is indeed copper. And now let's write down the reduction half reaction. Remember, guys, the reducing agent does not undergo reduction. The reducing agent undergoes oxidation. Cool. So now what is the reduction half reaction going to be? I hope you guys have your table 4B present. What is the reduction half reaction? So for this one, the reduction half reaction is going to be O2 plus 4H plus 4 electrons goes to 2H2O. Thank you to everybody that tried. Let's actually go through why exactly we have this as the reduction half reaction. Remember, the reducing agent does not undergo reduction. The reducing agent undergoes oxidation. Okay? So if you know that your reducing agent is copper, that means your reduction half reaction has to be the other thing. But now let's actually get into how we determine stuff like this. So first and foremost, I'm going to give you guys a general approach on how to just tackle galvanic cells in such a manner that we do not lose out on marks. We need to remember that um, okay, hold on. The reducing agent undergoes oxidation, guys. The reducing agent undergoes oxidation. The oxidizing agent undergoes reduction. Anyways, so let's go through how I would go about doing electrochemical cells, specifically the galvanic one. We know that the cell potential for a galvanic cell needs to be greater than 0. That's the first thing. We know it's greater than 0 because it's spontaneous. Spontaneous redox reactions have cell potentials greater than 0. To the to the person who was explaining, okay, I'm note to that. So with the cell potential, we should recall it as being equals to my cathode electrode potential minus my anode electrode potential. Okay, and that still needs to be greater than 0. That's step 1. Step 2 is I'm now going to find my electrode potentials for what I've been given. I have copper, and the copper 2 plus, I have water, I have oxygen, and I have the H plus. Let's get the electrode potentials for that. So for the copper 2 plus, if I go on my table, I'll see that it's going to be 0.34. For the other half cell, I'll see that's going to be 1.23, positive 1.23. Let me write that down, actually. And now, if I want to figure out which one's the cathode and which one's the anode, firstly, I can just do the cell potential thing. I know that if I take the difference, it has to be positive. So I know that it's going to be the bigger one minus the smaller one. Okay? And that is indeed greater than 0. And now I know that my cathode is the thing with the water. My anode is the copper. Right. So I'll probably do this as step 1, and I do this as step 2. Step 3 is just recalling the following. We have red cat and an ox. Red cat tells me that reduction happens at the cathode. So with that in mind, if I now figured out that the water side is the one that's undergoing reduction because it is the cathode and it follows red cat, I can then now answer 8.2.4 in that manner. Are you guys with me so far? And then the other side also applies for an ox. Oxidation happens at the anode. I figured out that my anode is copper. Okay? So that's how I would approach this in terms of figuring out what's the cathode, what's the anode, where's reduction happening, where's oxidation happening. Are we good so far? Lovely. Now let's move on to 8.2.5. Let's get the balanced ionic equation for the overall cell reaction. So for this one, I don't consider it to be a difficult question. The balanced ionic equation for the overall cell reaction will be the following. It's going to be, well, first you write copper plus O2 plus OH plus. I put my single arrow, and that becomes Cu2 plus 2H. Oops, sorry about that. plus 2H2O. And now I need to balance. Okay. If I balance, I know that I need two coppers here and here. Remember, when I balance in terms of the electrons, the number of electrons being transferred. Okay. The copper half reaction deals with two electrons. The one with the water and the oxygen and the H plus has four electrons. So I know that this has to be times two to have the same number of electrons being transferred. Okay. Yeah, I see somebody already answered that in the chat. Well done. That's actually great. So yeah, that's how we would do 8.2.5. Are we all clear on this? Do you have any questions? Can we move onwards? How did I know that I take copper solid instead of ions for 8.2.3? Oxidation. Okay, so in this case, we're losing electrons. So copper is undergoing oxidation. So it starts as copper as a solid, and then it becomes copper 2 plus 2 electrons. So we're starting on this side. That's why I'd have copper as a solid. Hopefully that makes sense to the person who's asking that. Let's carry onwards. Let's move on to 8.3. 8.3, here we're told that the graph shows the EMF of the cell against time. Let's calculate the value of X. The value of X is the EMF. To the person asking the question, we don't include platinum for the ionic equation for the overall cell reaction. Platinum does not react. You would include platinum in the cell notation, though. They didn't ask us for the cell notation for this question. Cool. Let's get the value of X, the EMF of the graph. What do you guys think that would be? This one I think is a simple one. You guys can do that. What is the EMF? Or in other words, the cell potential of this galvanic cell? In our case, it's going to be 1,23 minus 0,34, which gives us a value of 0,89 volts. That's the answer to 8.3.1. Let's go to 8.3.2. Let's explain the decrease in the EMF of the cell as time proceeds. So for this one, the EMF decreases because the concentration of reactants also decreases. So in other words, our cell is reacting, we are nearing equilibrium. As we near equilibrium, the concentration of reactants decreases. Okay? So for 8.3.2, I'd say over here, the concentration of reactants decreases. Cool. And now at 8.3.3, they're asking what has happened to the reaction in the cell at time t1. What do you guys think has happened at t1? Let's see, are we all on the same page? Do we know what has happened at t1? Yes, the reaction has reached equilibrium, or in other words, it is complete. So I'm just going to write over here, equilibrium reached. Okay. So that's question 8. Now, in the last stretch, Let's go on to question 9. Question 9 tells us that the diagram represents the apparatus used in the electrolysis of concentrated sodium chloride solution. A and B are two carbon electrodes. 9.1.1 asks us to define an electrolytic cell. An electrolytic cell is a cell in which electrical energy is converted into chemical energy. Cool. Now let's go to 9.1.2. Write down the half reaction that occurs at electrode B. How do you guys think we now approach or tackle this one? So for this one, remember guys, let's look at how our electrolytic cell is set up. I firstly want to ask, with the power source, let's see if you guys can recall. Is the long side positive or is it negative? Is this here positive or is it negative? That is correct. B is positive. So here we have positive, over there we have negative. Cool. Since we have sodium chloride solution, what then happens is that the sodium chloride, rather, let me do it on the side. Sodium chloride dissolves and we have Na plus and we have Cl minus. Okay? With this over here, my next question is, would the sodium go to electrode A or B? Will the chlorine go to electrode A or B? Okay, the answers are coming in. Sodium will go to electrode A, the chlorine goes to electrode B. That is correct. In this case, you can think of it as like the opposites attract. So we know chlorine is at electrode B. So let's write that half reaction. What's happening over there? Is the chlorine undergoing reduction or is it undergoing oxidation? For 9.1.2, our chlorine is indeed undergoing oxidation. We have chlorine minus goes to become Cl2 plus 2 electrons. Let me balance it. Let me write my phases over there. And that's what we have over there. The chlorine does indeed lose the electron and it becomes chlorine 2 or Cl2 as a gas. Okay, seems as though we're all clear on that. Let's now go to 9.1.3. Or rather, let's decide now. Is electrode A or B? Or tell me in the chat, which one's the anode, which one is the cathode? Which one is the anode, which one is the cathode? You need to remember red cat and ox. So reduction happens at the cathode, oxidation happens at the anode. That therefore makes electrode A the cathode and B the anode. We know B is the anode because chlorine is losing the electrons. So I'll have anode over here. And then over here, I have cathode. Okay? Cool. And now let's go to 9.1.3. Let's write down the name of the formula of the gas formed at the cathode. Bubbles observed at the cathode. What gas is being formed at the cathode? Answers are coming in. Remember, guys, chlorine is being formed at the anode. Remember, we just figured out that chlorine is being formed at the anode. So that can't be the answer to this question. This over here is for the anode. So the answers are coming in. It is indeed hydrogen gas. Hydrogen gas is being formed. And now let's get into the reasons why. Let's get into the reasons why that is. So remember, we are told that this happens in an aqueous solution, right? This AQ tells us aqueous solution. So there is water present. Okay. And now with water present, we also have to consider the relative oxidation agent strengths of what's going on. So let's do the following. You have to remember firstly, H2O is present because NaCl in an aqueous solution. Oh, I misspelled that. Let me rewrite it properly. Cool. Let's get the electrode potential of H2O. Let's find that. Let's get the electrode potential of sodium. What's the electrode potential of water, guys? Let me find this earlier. I swear we did. Yeah, I'm just going to have 1,23 there. And then for sodium, that is going to be minus 2,71. I'm just going off the actual values here from the table 4B. What we should note is that water is the stronger oxidizing agent. What I mean by that, if it's a stronger oxidizing agent, it will undergo reduction more easily. And that's why we have hydrogen being formed there. Okay. And then in the follow-up, I'll just have H2O reduced to H2. This one doesn't apply actually. I think I've selected the incorrect water electrode potential. Could one of you find the accurate one for me, please? And then I can actually fill that in. But this is how we would answer this over here. We have to now recall and remember that if it's in an aqueous solution, water is present. And now we have to look at the relative oxidizing agent strengths and see which one will more easily undergo reduction. In this case, it is water. And that's why water would reduce to H2 more easily than our sodium ion reducing to become the sodium as a solid, isn't it? Okay. So that's what we have for this question over here. How are we so far? Okay, do you wanna at least get the okay, 1,77. There we go. Thank you so much. Let's now see question 9.2. Do you have any questions on what we've covered thus far? Can I get a thumbs up if you can move onwards? Any questions? Okay, great. Um, Now let's move on to 9.2. We are told that an electrolytic cell using an impure copper electrode consisting of 95% copper and a pure copper electrode um, is present. So copper 2 chloride is solution is used as the electrolyte. 9.2.1 asks, is the pure copper the cathode or is it the anode? Okay, so the answers are rolling in. This over here, pure copper is going to be the cathode. Pure copper is the cathode. Okay, what we should be recalling, or what would help us greatly when figuring out questions like these, would be the following. So when we have an electrolytic cell like this with the impure and a pure, the impure one is what breaks down. Okay? Because we kind of refining it, right? You want to break down the impure, and then you want to build up the pure one because you're refining it. So I'm just gonna write in quotation marks, the impure breaks down, the pure builds up. Okay? If we have copper, right? We either have one of the two happening. We'll have copper as a solid that oxidizes, it becomes copper 2 plus 2 electrons. And then you have copper 2 plus in an aqueous solution, plus the 2 electrons, and that becomes copper as a solid. Okay? So when you say the impure one breaks down, this is essentially what's going on. Change the color. This is what's essentially happening at the impure one. It breaks down into the aqueous solution. And then at the pure one, at the cathode, it builds up into that. Okay? Wherever your cathode is, you usually have mass being deposited over there, or you have the electrode increasing in mass. What helps me understand this is oxidation is loss. At the anode, oxidation happens. And if I say oxidation is loss, I can expect a loss in mass, essentially. I have red cat. Reduction is gain. If I'm gaining at the cathode, I can expect to see the cathode increase in mass. You don't necessarily remember this as a hard rule. The whole point is to learn all of this and kind of understand it and apply it on a case by case basis. This is how I would kind of decide or figure out that the pure copper is the cathode. To those who didn't get that correct, do you understand now? Are we good? think I'm only seeing like a couple of thumbs up. So just want to make sure everybody's good and solid on this. Okay, great. Now let's look at 9.2.2. When all the copper in the impure copper electrode has been deposited on the copper electrode, it is found that 6 moles of electrons were transferred. Calculate the mass of the impure copper electrode. Okay? So we know that 6 mole, 6 mole of electrons transferred. Let me try to spell this properly. Yeah. How do you now relate that 6 mole to what they're asking? What can we do with the 6 mole? So firstly, we have to now look at the ratio of electrons to copper, the copper ion. Okay, I'm just going to rewrite the copper half reaction. I'll have, hold on, Cu2 plus 2 electrons goes to, okay, it might be more, to be more accurate, to be 100% accurate, let me do specifically for the impure electrode. So I'll have the following then. Okay, now that I have the following, let's look at the ratio of electrons to copper itself. You'll see that it is a 1, or 1 is to 2, essentially. So I have a ratio of 1 is to 2. Let me just have 1 Cu for 2 electrons, and I have to use this now, okay, to inform my answers. In this case, if I want to get the number of moles of copper, to get that, that's just going to be half times 6. The 6 comes from the moles of electrons. And so the moles of copper in this case is just going to be 3 moles. Are we good on that so far? I looked at the ratio between electrons and the actual copper. In this case, I'm doing for the impure copper electrode. Okay, great. Seems as though everybody's on the same page. And now I know I have 3 moles of copper. Now let's get the initial mass of the impure copper electrode. For that, I have to use the following formula. I have N is equals to mass, or mole is equals to mass over molar mass. My mass in this case, I don't know. My moles, I do know. My molar mass, I can find out. So my mole is 3. My mass, I don't know. That's my unknown. My molar mass, I can find out. If I look at my periodic table, I get my molar mass as 63.5 grams per mole. If I solve for my unknown variable, my mass, I end up with 3 times 63.5. And that then gives me a value of 190 5 grams. Yes. Cool. Now, let's go back to the question itself, right? Let me zoom out a bit so we can see everything. Remember, they told us that it's an impure copper electrode consisting of 95% copper. So how do you guys think we can use that to get the actual um, mass of impure copper? Because you know this impure copper is 95% copper. So how do you guys think we get this? Any ideas? Maybe I can give you guys this as a challenge. Let's get the initial mass of the impure copper electrode. Try get that. Try calculate the initial mass of the impure copper electrode. When you guys get your answers, please, please, please post them in chat. Okay, answers are rolling in. I'm seeing 2 answers. Um, let's see. In the meantime, I'm gonna answer the questions in the chat. Somebody asked if they are asking to calculate the initial mass, but for the pure copper, um, the half reaction is going to be reduction, not what you have written. It's essentially the same reaction. It's still copper. Copper oxidizes and then reduces again. So they're not too specific about it for this simple question. You don't even have to write it out. I'm just doing this for the sake of explaining where exactly I'm getting that half from, why exactly I'm doing what I'm doing. I just wrote the half reaction to show it and then be like, oh, so you guys can see that, oh, I have 1 copper for every 2 electrons. To see the ratio of 1:2, and then I use that in the following step, whereby to get the actual moles of copper, it's going to be half times 6, or in other words, 6 divided by 2 to get 3 moles. So I've kind of answered 2 questions at a go with this. To the person who was asking about where the half times 6 come from, half times 6 is the same as 6 divided by 2. And I get that from the ratio over here, this ratio. 1:2. Okay. Um, yeah, hopefully that tracks and you understand. So yeah, let's carry on. Let's look at the answers for this one. Um, I'm seeing a range of answers. I'm seeing most of the same answer, and then I'm seeing a couple answers deviating. So for this one, to get it, we know that the total mass, right? So let me write M impure. The total mass of the impure copper electrode, 95% of this will give us what we worked out above. So in other words, M times impure times 0.95 is going to be equals to 190.5 grams. So to get the actual mass of the impure, that's going to be 190,5 divided by 0,95, which then gives us a value of 200,5 3, not 55, 53 grams. That's the total impure mass initial. That's the answer to this question. Answer the questions in chat. Is the amount of copper in the cathode the same as that in the anode? No. If you're talking about the actual masses of the electrodes, no, they're not the same. If you're talking about the transfer, I guess kinda, the amount of mass that the impure loses, well, actually not even. The amount of mass of copper specifically that the impure loses is equals to the amount of mass that the pure electrode gains. But the total mass lost by the impure electrode, that total mass loss includes the copper as well as the impurities. The impurities will likely settle to the bottom of the cell over there. Hopefully that answers your question. When you say you don't understand, I please be specific. I would like to help you. I'd love to help you, but I'm not even too sure what I can say. So please be specific about that one. Let me see if there are any other questions. Somebody did ask earlier about the differences between electrolytic and galvanic cells. I'll do that once we are fully done with this. This is the last question of the session. So I think now is Q&A time relating to the work we just covered. You don't understand the last part of the impurity. Okay, so let's read this right here. We're told that an electrolytic cell using an impure copper electrode consisting of 95% copper is used. Okay, I'm going to stop there for now. Now, in this case, what we calculated was the amount of copper transferred from the impure electrode. We know that, the amount of copper transferred from the impure electrode is the total copper contained within it. Okay? But we know that's not the total mass of the impure electrode. The total mass of the impure electrode, M impure, if I multiply that by 95%, I get the total mass of copper that was originally contained within that. So that's why I have M impure, mass impure, times 95% is equals to 190,5 grams. And now to get the mass of impure, I divide 190,5 by 0,5, and I see that my mass of impure is greater than the actual mass of copper contained within it, which makes sense. If I have, I don't know, I can use maybe jewelry. Let's use silver, right? Sterling silver is 92.5% silver, if I remember correctly. The total mass of silver within sterling, 92.5% silver, that's going to be less than the actual mass of the measured silver ingot that they give you. Are you with me? We just told that 95% of the actual impure mass is copper. The rest is just impurities. Okay? Hopefully you understand that. Yeah. In the meantime, I can quickly go over the differences between galvanic and electrolytic. Galvanic cells convert chemical energy to electrical energy. Electrolytic converts electrical energy into chemical. We know that for electrolytic cells, such as this one, you have one cell. Whereas for galvanic cells, such as the previous, well, we only give one. It's fine. So galvanic cells such as this one, well, it wasn't sketched. We have two half cells. A galvanic cell looks like the following. You have half cell 1, half cell 2. You have your salt bridge. You have your electrodes. and then maybe it's connected to like a voltmeter or something like that. So if you remember, the function of the salt bridge is to maintain electrical neutrality, completes the circuit. I may be missing one more, but that's essentially that. And yeah, whatever you remember of an electrolytic cell, a galvanic cell is basically the opposite. Basic, not entirely, but basic. In this case, for a electrolytic cell, we know that the cathode is negative, but for a galvanic cell, cathode will be positive. So it is a matter of going through the stuff. I did do electrochemistry revision, I think maybe a month ago or like 2 weeks prior or something. I go through it in depth. You can find it on our YouTube channel, which is at the Learning Space ZA. Please do go through it. You will find this session as well as the previous session and others that I will do and have done on our social media channel. But for the moment, if there aren't any, well, hope the floor is your guys's to ask questions now. Yeah, the page name is at the Learning Space ZA. Please do check that out. Do we have any other questions relating to what we've covered in the session? It's at the Learning Space ZA on YouTube. I think that might be the handle for everything. But yeah, that's what we have for now. How are we feeling now that we've reached the end of this second chemistry session? Chemistry tends to scare a lot of people. Hopefully, we enjoyed the session and we did find it useful. 8.3.1 is this over here. That's 8.3.1. Thanks for joining, guys. Please do give us a 5-star review on Google. We would greatly appreciate it. It just encourages us to keep on doing what we do. But also make sure that whatever we're doing right, we continue doing that. Okay? I do hope you guys have found it very beneficial. Maybe in the chat, quickly tell me what specifically do you know more of now? Or do you feel slightly more confident about? Please, guys, give us the reviews. We would, I'd greatly appreciate that. We would all appreciate it. What topics are you finding easier to manage? What topics helped you? If there are topics that you are unsure of, do check out our YouTube channel. We do have a lot of topic breakdowns, a lot of revision over there, a lot of other past paper walkthroughs with me and the rest of the team. Please do join us for the rest of our sessions that we have. Yeah, the rest of our sessions will prove to be useful. I will be doing physics paper 1, should be starting later this week. I do know that we also have maths papers being run on days that I don't present the sessions. So yeah, thank you so much, guys, for taking time out of your day to come and watch chemistry and participate in chemistry. We will be doing paper 1. So do check the schedules if that has been published, but check our socials. We also do post what we're doing and what we're going to do on our socials. Electric circuits, we'll do that in the session during which we do paper 1. That is our next session, I think on Thursday. Yeah. Thank you so much for joining, guys. Greatly appreciate you guys taking time out of your day to sit and do chemistry. Hopefully, you guys have found my explanations helpful.